Hello, welcome to this lesson on how to use the inertia tensor to find the inertia or moment of inertia of a system of particles. Okay, rotating about an axis. The moment or the inertia tensor is actually used to calculate for the moment of inertia when your system is rotating about an axis. Once again, if you have not subscribed to my channel, kindly subscribe to support the channel. Okay. Alright, so let's read the question together. Given a system made up of three particles with masses and positions, okay, so we have these for the masses and positions. So the first one is of mass 1.5 kilograms with a position of 9, 2, and I hope you know what is position. It means that the position R1 is the same as 9i plus 2j plus 4k. Okay, just that this is given in just row form. Okay, just how do you call it, a row vector form. Okay, likewise to this one, it has a mass of 2.5 kilograms and the position is given as this. Okay, and the last one is of mass 5.5 kilograms and the position 3a3. Okay, now using moment or some inertia tensor, right, find the moments of inertia of the system about rotating about an axis of this. Okay, so how do I go about this question? All right, so let me write the formula for you. Using inertia tensor, this is how the formula looks like. The moment of inertia I should be equal to um n, okay, n transpose. It can be any n transpose times or dots. This is a multiplication, normal multiplication, okay, times the inertia tensor, okay, and I'll write the inertia tensor for you times n, where n dot n is equal to 1. Okay, so meaning that n here should be a unit vector because that is the only vector that it dot product or the dot product of it itself will give you 1. Okay, and then the inertia tensor, let me write it well. The inertia tensor, let's say it is given by, okay, so this whole big matrix here, and we have summation mi in the first row, yi squared, okay, so yi squared plus zi squared, okay, then the next entry is okay, I think I have to write it also because other than that it won't go here. Okay, other than that it won't go here. The expression inside is very very plenty. Okay, so inertial tensor, the it, that is whatever that is inside here should be equal to summation, okay, mi, then yi squared, okay, plus zi squared. Okay, first entry in the first row, then go to the second entry minus summation mi, okay, xi yi, okay, go to minus summation. I hope you seen how the format is going. Mi, okay, then automatically you will get a zi somehow. Okay, so minus summation mi sorry, xi rather. Okay, xizi. Let me put it like sz. Okay, when I write yz, I want it to be able to go here, so or want to write it here, so please bear with me when I don't bring the i's. Okay, then here will be minus summation mi. Okay, so let me make it m, then x, or let me yx rather, or xy, anyhow you want to call it. Product is commutative, so multiplication is commutative, so xi is the same as yi. So I want to write it like this. It was supposed to be yi, but let me write it like this. When you come to the second entry here, it becomes summation. This one is positive mi, then xi squared plus zi squared. Okay, but I said that I want to be able to write everything here. That is why I didn't bring the i's. Okay. Then the next one will be minus summation m y z. Okay. Then it goes to this minus summation zx, but here I can write what xz since it's just multiplication, but there's an m here. Okay, kindly bear with me. It's very plenty. Okay, mxz, then minus summation myz, then you come here summation m into x squared plus y squared. But here, remember that we have mi, there are i's attached to them, but for simplicity, sorry, for us to be able to simplify it clearly or to get it clearly here. So, like I said, for simplification cases, let's try to write it like this. But in our mind, let's put it that there's an I. All these are i's here. Okay, meaning they can be varying. Okay, so this is the inertial tensor. This is the tensor we are going to use. Okay, and the n that I said we should use should be this. Okay, and the n is the axis that the system is rotating about. Okay, so let's go to our question. You can see that the system is rotating about this axis. Okay, and the axis is giving us 2 comma 6 comma 3. Okay, so this is the axis, but the question is, when I dot this by itself, will I get 1? No, because this dot itself is 4 plus 36 plus 9, and this is 49. Okay, it doesn't give me 1, so it means I have to change this to, for my idea in vectors, I have to change this to um an axis that I can get 1 when I dot it by itself. So the only thing I can do is I call this, let's say n, let me call this n. Okay, let me call this n to be equal to 2 6 3. Then I find the unit vector across this or along this. Okay, and that will be just the same. The unit vector across this is n cap and is the same as n over magnitude of n. Okay, I hope you know how to find the magnitude of n. All right, so let's go ahead and write everything down here. Okay, we know that our n, he said our n, we have to use the n cap rather, because when you dot n you don't get 1. Okay, so it's equal to n over magnitude of n, and this is giving us 2 6 3. I hope I'm right. Okay, I hope I'm really right. Okay, 2 6 3 divided by magnitude of all these is just the square root of the sum of the squares inside. Okay, meaning the square root of 2 square root is 4 plus 36 plus 9. Okay, and this will give me 2 over 7. Okay, 6 over 7, 3 over 7. Okay, and now if I dot this by itself, I'll get 1. So it means I should actually use the unit vector along this to compute for my inertia. Okay, and then with the inertia tensor, you could see that there's this thing here, summation mi squared plus zi squared. We have all these, so we have to compute for all of them. Okay, so first of all, we pick summation mi, okay, yi squared, okay, plus zi squared. So what you can do is you go to your question given, you write your mi's and the rest. Okay, so you know that for the first time, let me first write them first before you come here. Okay, because other than that we won't get anything to refer to. Okay, referring to the question sometimes become very difficult for us. Okay, so for m1 equals 1.5 kilograms, okay, kg, we have a r1 to be equal to 924, and for m2 equals 2.5 kilograms. Okay, we have a r2 to be equal to 137, and for m3 equals 5.5 kilograms. Okay, you have R3 equals 3 comma 8 comma 3, and these are for our position vectors. Okay, so for the first time you have to go and find summation in the matrix. You have to find this. Okay, mi yi squared plus zi squared. Okay, it means that since we have three matrix or three position vector, we have to move from I equals 1 to 3. Okay, so when I equals 1, you have m1 y1 squared plus z1 squared. Okay, then you go to m2 y2 squared. Okay, plus z2 squared. Okay, let me write it well. Z2 squared. Okay, plus m3 y3 squared plus z3 squared. Okay, now you go to position vectors. Our mass 1 is 1.5. Okay, y1 is very simple. Y1 is 4. You go to your, just refer to your listing of your position vectors and you know what I'm trying to say. So y1 squared is just 2 squared, that will give me 4, plus z1 squared, and that is 4 squared, which is 16, plus 2.5. Okay, so you go to the next position vector, you pick your y2, square it, then z2, square it, like that, plus 5.5. Okay, into 64 plus 9. Okay, and this should give me 576. Okay, 0.5. I hope you can see this. Then you go to the next one. So these are my position vectors I'm referring to. Okay, so the y1 squared is just this square plus z1 squared, that is that, times the minus 1. Okay, so you move ahead and you find our summation. You have somewhere you have mi xi yi. Okay, and this should be equal to, for m I equals 1. Okay, so I have mass 1, which is 1.5, times x1 times y1. Okay, and x1 is 9, y1 is 2. When I multiply them, I'll get 18, plus, like that. So you move to the next one, then x2 times y2, which is 1 times 3, and that would be 3. Okay, then plus 5.5. Okay, 5.5 into x3 times y3, and that is 3 times 8, which is 24. Okay, so this will give me 166.5. Okay, then we go to summation mi zxi. Okay, if you remember, I'm just trying to find the element inside the inertial tensor. Okay, so looking at here, we have this here, we found this, and now we are here. Okay, but if you could see, this is the same as this one, so if you are done with this, it means we can also find this. Okay, they are the same. All right, and also with the z and x, this is also the same as this. Okay, so once we are done with that one too, we'll be able to use it as well. Okay, so it means this one is also equal to 1.5 into 36. Okay, just multiply x1 and z1. Okay, plus 2.5 into 7, that is mass 2 times x2 and z2, plus 5.5 into 9, and this should give me 121. Okay, then I'll go ahead and find my summation. What element again? Mi xi squared. Okay, plus yi, oh sorry, zi squared rather. Okay, and this should be equal to 1.5 into 81 plus 16. I hope by now you know what we are doing here. 2.5 into 1 plus 49. Okay, plus 5.5. Okay, into 9 plus 9. Okay, and this should give me 369.5. Okay, then I move to summation yi, oh sorry, there's an m here, m yi, okay, zi, and this should be equal to 1.5 into 8, okay, plus 2.5. I hope you can see this, okay, into 21 plus 5.5 into 24, okay. What this means is just simply multiply y and z in every position vector you get, okay. You multiply them, then you multiply it to the mass at that position vector, okay. So this is equal to 196, okay, 0.5. So the last one we should find is summation mi x squared or xi squared plus yi squared, okay. And this should be equal to 1.5 into 81 plus 4 plus 2.5 into 1 plus 9 plus 5.5 into 9 plus 64. And this whole thing should be equal to 554, okay. So now we've gotten what we need, okay. You've gotten what we need. These are all what we need, okay. So it means that my inertial tensor it is now equal to, so I go to my inertial tensor matrix, wherever I see summation whatever, then I put it there, okay. So this, we know the value, we know this. We say that this and this are the same, so we put the value for this one here, okay. Likewise, this and this are the same, and the same thing happens to this and this, okay. All right, so we move ahead and go to our matrix, and the values that we got, okay, for the first entry we had 576.5, and there is a minus in front of the second one, so 166.5. Then we have negative 121, okay, negative 166.5, 369.5, negative 196.5. Then you have negative 121, you have negative 196.5, and 554, okay. And we said that the inertia, moment of inertia, is being calculated from I is equal to n cap, or this time you're using n cap, so n cap transpose it, all multiplying, okay, n cap. And now we will have to make sure that the multiplication is correct, okay. Now the n cap given here is equal to 2/7, okay, 6/7 and 3/7, okay. Now if I transpose this, I will get a 3/1, and if I multiply it to this matrix, which is 3/3, it won't work, okay. It won't work. So I have to make sure that I interchange them, okay. So I'll rather call my n cap, okay, to be this 2/7, 6/7, then 3/7, and my actual n to be equal to, or my actual n cap, this is my n cap, okay. If you use this and you transpose it, like I said, it will give us a problem. So you actually have to call this n cap to be the column vector rather, okay, 6/7 and 3/7, where the transpose, or the transpose of it, will give us this, okay. So n cap transpose should be this, for us to be able to be safe, okay. Always when you are multiplying, this is how you do it. So now with this one, with this thing there, then what we have to do is I will then be equal to, we said we are choosing n cap transpose to be this 6/7, 3/7, then multiplying our inertial tensor, which is 576, okay, 0.5, negative 166.5, and we have negative 121, we have negative 166.5 again. We have 369.5, and we have negative 196.5, negative 121, negative 196.5, and we have 554 multiplying 2 on 7, 6 on 7, and 3 on 7. Okay. Now, if you do this matrix multiplication clearly, you get your inertia, moment of inertia of this whole system using inertia tensor should be 164.73469. Okay. Like I said, you should always know your unit, kilogram meter squared. Okay, so this is the moment of inertia of the system using inertia tensor. I hope you understood the process. Take your time and go through it, digest it, and know how to go about it. Okay. All right. Thank you. And once again, don't forget to subscribe to my channel if you have not subscribed.